Okay, hello. Um, this video is a tutorial on how to analyze a simple frame, which includes a beam held by two columns. Now, let me share my screen with you. Hopefully you can see my screen. Now, I begin from the very first beginning step that you should take to draw a frame and define the different elements in Karamba and then analyze the frame. So the first step is to draw the frame, and basically you can get started by giving a base point. I'm going to input all the dimensions in meters. And before doing that, I will make sure that the units are correct here on Rhino. It's a pity that if you want to analyze your frame using the English units using Karamba, everything will be really messy. And I really don't recommend to do that. Of course, there is always a component that you can set the units to English units, but you will never come up with a very reliable result, because at some point, again, the outputs will be in kilogram, the displacement will be described in centimeters, so it will be very crazy. So just go with meters. So I will make sure that the units on my Rhino model is in meters. Then I get started to draw a line. So I draw a column with the height of um, 3 meters and 40 centimeters. So it will be 3.4. And then the length of the beam can be like 5 meters. And then there will be another column, 3.4 meters. So this is our basic model of a beam held by two columns. Now I will pull up the grasshopper panel here, and the first thing I do is to double click on the that grasshopper window and type curve. There it is. And you can right click on the curve and just give it a name. So I want to write it at the beam. And then I make a copy of the same curve. You may call another function for curve. So I just rename it by right click on that and say column A. And this one is column B. And I will assign the lines that I drew to these functions. So I right click on beam, say set one curve, and I will click on the beam. And then you see it turned to be gray. So it's not orange anymore. That means this beam is assigned to our curve here. Now for columns, again, I right click on column A, set one curve. I pick this line as column A, and then I will set this one as column B. Okay, now I have 3 curves defined in Grasshopper. You're more than welcome to create the curves in a parametric way using different functions by defining 2 points and draw a line between them. But just for like simplifying the whole process, I will just draw the model on Rhino and then assign it to the curves that I want to analyze in Grasshopper. Now, the next step is going to the Karamba page. If you go to the Karamba plugin, you will see here that there are various tabs. The very first one is like the model tab, where you can actually use the different functions and drag, click on them and pull them into your model view. For example, I want to define a beam. So first of all, I need to define for Karamba that the line or the curve that I assigned to my model is a beam. So I click on line to beam, and there you'll see that here I get a function. So first of all, I want to define the beam. Well, basically you can attach all the different curves to all together to line. If you want to attach more than one curve to this line, you should hold shift, and then you will be able to connect 3 different curves to this input part of the line to beam function. Now I want to give each of these curves an ID. So you can go to like the very first tab of Grasshopper, or you can just simply say key in panel. And when you type in panel, or you go from the input part and get the panel and drop it here, then you can right click on the panel and set it as multi-line data. Okay, when you do that, then you will be able to like make a list of items and give a name to like multiple data. So I will say the first one is going to be the beam, then the second item will be column A, then the third will be column B. Okay, so here you will see that each of these names are assigned to like an itinerary, a list. So 0 is beam, number 1 is column A, number 2 is column B. Then I'm going to attach it to line to beam. One thing here that is important is to make sure that you connect these curves in order, in the same order to this line to beam function. So I will first connect the beam to the line, then I will hold the shift and then connect column A and then column B. With the order that you connect these curves to line to beam, they will be assigned to this ID, these IDs. So beam will be assigned to the first item, column A will be assigned to this curve, and column B, ID column B will be assigned to column B. Okay? Now, you defined both your beams, your beam and both columns as beams, which is okay. In Karamba, you can either define your model as either beams or surfaces. Okay, wherever you have beams or frames or trusses, you should define all the lines to beams. Or wherever you have surfaces, you can just refer to them as a surface and define a mesh. So now in this tutorial, we're going to just work with beams, and columns are a different source of beams, but they're like loaded differently, so that's okay. The next step is to assemble a model. We want to make a structural model. So the first step is to define that element, which we already did. The next step is to define supports. Okay, we go all the way through this list. So in order to define the support, you should go to the model view. Let me maximize the size of my grasshopper screen here. When you go to the model tab in Karamba, at the very bottom, you can find support. You can also double click on the grasshopper screen and just type support, and then support for Karamba 3D, this one will pop up, okay? So either way, you can pull up the supports. So we're going to have one support at the bottom of the first column and another support at the bottom of the column B. So let's just make a copy of this and define the two supports separately. To define the supports, you need to define the point at which you want to place that support. So what I'm going to do is to find the end points of the lines that I drew. So I would say I first attach column A to this. I will just double click on the screen, typed end points. When I type end, endpoints pop up, and then you can click on that. So this function will give you the two ends of a given line. Now, for column A, we want to get the initial point, which is 0, 0, 0. So I will connect that to the support, okay? And for column B, I will take the end point of that line and connect it to the support, okay? Now, I want to define the support conditions. I will make sure that my support, both supports, don't allow any sort of transitional movement. So I will fix the TX, TY, TZ and say, well, these three should be fixed. That shouldn't allow any movement. And also, I will click on RX. To like restrain any rotation along the x-axis. So, and that is sufficient for one support. So then here, I will attach the supports to my assembly. So I will hold the shift and connect both supports to this support input at the assembling part, assemble model. The next step is to define the load. I want to load this beam, right? The second tab in Karamba is load. You can either define loads by just their characteristic, like gravity load or so forth and so on. For this particular simple model, we can just define a load for a beam. So I would just click on beam loads and drop it here. Okay, as you see here, the loads can be concentrated, can be block, and that block means distributed load. So it can be a distributed load or like trapezoidal loads, but by block load, we mean uniformly distributed load. So let's just define a concentrated load, a point load, also a uniformly distributed load, just to practice, okay? So here I will define a point load and a block load. To define that load, I should define this load. What is actually the name of this load, and what is the magnitude of this load, and at which element this load will be applied. So let's first give them a name. Well, I will say a point load. point load 1, because you can also define multiple loads. Come on, springs. Okay, so this is it, and I'm gonna have another load ID, so I would say uniformly distributed load 1. Okay, yeah, come on. Okay, anyways, so here it asks for name of the load, so I would say this will be a point load, and the other one will be a distributed load. And now I want to set the point of application of that load. So again, I need another panel, and I want the load to just act on the beam. So I just want to load the beam, but not the columns. Of course, you're more than welcome to, for example, define a lateral load for the columns and analyze the frame while being loaded by, for example, a wind load or so. But here in this simple example, we just want to load the beam. So, and here we gave an ID to our beam. The ID was beam. You can even call them A, B, C, or 1, 2, 3. I mean, depending on what ID you already gave to the curves, you can call them here. So by just typing in beam, I will say that the load should be applied to the beam, only to the beam. Okay, there you are. Now I want to set the magnitude of that force. Well, you can double click on the screen and just make a slider. So my load can be upward, downward, and with different like magnitude. So I would just make a slider of -10 between 10, -10 by 10. So that load then it can be downward of maximum of -10, or I mean then it can be a -5 or whatever, and then it can be like 0 amount of load, and then it can be upward like 5, 8 to 10. Okay, for now for the point load I would just set it to -10, and I cannot connect that magnitude to the force input value, because what we need is to define a force vector. A force vector includes a magnitude here, which we define it by the slider, and it also needs a direction. So we should call a vector. You can just type in z vector. Here you will see that one function pop up, which is unit z. This unit z is actually a vector along the z-axis. And basically, I want to have like a vertical downward point load along the z-axis. So that's why I call the z-vector. Then you connect that vector to the force. Okay? And then you'll do the same thing for the distributed load, and this time you would say, you can say the force is -10, or let's just say -6, and then that will be the distributed load. Now again, I'm going to connect the loads to my model, and to make sure that both loads can be connected, I hold Shift on the keyboard and connect both loads to the assembling function. Then the next part is defining the cross-section. To define the cross-section, we should first figure out or let's say we should first determine which material you want to use. You want to use a wood material, steel material. What is your material? And then select a particular profile as a cross section of your beams and columns. So by going to Karamba here, you will see there is a material tab here. If you click on that, it says material properties, material selection, and blah, blah, blah. Material properties is useful when you want to define the different properties of a particular material. I mean, imagine that might be spaghetti. But for material selection, you can just say here, material selection, and drop that function here. And then by clicking on select, you can select a family of materials. I would say steel. I choose steel. And then among the steel, you can make a choice. Which type of steel you would like to pick. I will choose S235, which has a quite nice stiffness. Again, you can give some names. For example, you can say steel type 1 if you're going to use with multiple different steel materials. But I mean, it will be just one category for this model, so I just keep it as it is. And then for the cross section, I go to the cross section tab and select cross section selector. Okay, so here we go. Here's the cross section selector. And also I will click on cross section range selector. We're going to use both of these. Why? Because here I said the material is steel, and that is the main category. So I'm going to connect that material here. Then when I select on the cross-section range selector, I can say which table of materials I want to explore. I will pick US, the US. I mean, there are like multiple different material tables for different countries. Let's just select the US. And then for the shapes, you may pick an I shape, which is basically the Y flange profile in the US. You can pick a box, a tube, whatever. So I will pick, let's say pick the I shape. And which family? So among the different I shapes in the US steel construction manuals, you can see like W shapes, M shapes, S shapes. I will just pick the simple Y flange profiles. And then I will connect that cross section to this cross section selector. Now what I need to do is to take a look at the tables that you have on the steel construction manuals. I posted a list of those tables on Brightspace. Let me stop sharing here, and what I'm going to do is to just show you some examples. Well, this is basically the example of the profile I showed you earlier during our lecture session, talked about the different material properties and cross-sectional properties of, for example, this Y flange beam. So I will like pull up one of these tables and just read the name of the profile that I want to choose. So if I want to go with a Y flange 27 by 178, I will just type in the same number, the same name in a panel. Let me again go back to the Rhino screen. Here, since we are just working with very minimal amount of loads, I just pick a very narrow profile, which can be, for example, W10 112. That is one of the wide shape profiles, steel profiles. And then I'm going to connect it to the name of that profile. Okay, so here if you move on and hold your cursor on the cross section, you will see it says one locally defined values, and that is a family of wide flange beams with that particular name. Then here I can either connect that cross section to my assembly model, or I can connect that to my beams. Okay, it doesn't make any difference. So here I define that my beams are all steel materials, and the profile is selected from the category of wide flange beams, and that wide flange beam is W10 by 112. Okay. The good thing here is that you don't need to convert any inches to centimeters because you're just basically referring to the name of the US steel profiles. Okay, so we define the cross section, we define the materials and the joint. So we have a beam held by two columns. We should define what is, how that beam is connected to those columns, and we should define the joints at that point, at that connection. So here there is another tab in Karamba, which is called joints. Here it says beam joint agent that define the connection of a beam to another element or node. So I will drop it here. Since I have two nodes, I will make another copy of that joint, and then I will define the joint. So in order to define that node or joint, I should say which element is going to connect which element. Okay, so here I have the beam. I want to say the beam I connected here. The beam will connect to column A. Make sure you type in the name, the ID of the members correctly. Okay, so there we go. And for the next joint, I want to connect the beam to column B. So add beam to column B. Okay, and that's all. You need to connect the joints to the assembly here. And I will again hold shift to make that connection. There we are. Okay, so this is what we actually built up as the Karamba structural model. Now the next step is to analyze that model. Okay, here at the algorithms, at the tab which is called algorithm, here you see analyze Karamba 3D. I will place it here and then connect the model to that analyze. Okay, now if you drop a panel here and connect it to the model, then you can read what was your model. You can say, well, I have a beam, I have 4 nodes, 2 of them were connecting the beam to the columns and 2 at the support, and I have 3 elements, I have materials, cross sections, everything is just simply represented here. And what's nice about this simple analyze tab is that the second item gives you the displacement of your, the maximum displacement of your beam regarding the two load cases that you have. Okay, you have two load cases, one here and one here. If you want to get the total displacement, you should just add these two together, but we're fine. The next thing is that, okay, this function analyzes our model, but we want to see the results. Okay, so I will just drop the model view from the results here, and then I connect the analyze model to the model view. Okay, if you connect the model from the assembly, then your frame is not analyzed, so you're not going to see any displacement or anything. So I will just connect the model that is analyzed to the model view. Now, here, you can open up these tabs and play around with some displaying scales. So for deformation, if you increase that 50, you will see that this tiny little red line will be exaggerated. If you want to see that deformation better, you can just simply click on this deformation and double click on that, and for example, type in 200. You see, that displacement is like more visible. Then, in addition to the display, there are some other tabs which you can play around with it that represents like the, what else? The cross-section elements. So you can click on the different tabs and just say what to be represented. Okay. The next thing that you can use to visualize your analysis is the beam view. Okay, there we go. This is the beam view. And again, I will connect this analyzed model to the beam view. Ooh. Now you can see that in the rendering setting, the cross-section is selected. So the profile that you selected, the steel profile that you selected will be shown here. And then you can even click on axial stress and see that the tension and compression stresses throughout the entire frame will be demonstrated. So as you expect, because this beam is under a kind of like gravity load, on the very top fiber of that, it will be squeezed, so it will experience compression stress, and on the very bottom surface, it will experience tension. This is a frame we haven't discussed that too much, or at least like let's say nothing about frames. But if we had discussed frames, you could see that in a frame like connected to the beam like this with a knot like that, that frame will, that column will experience compression on this side and tension on the other side. But you can just see that axial stress in your beam and column through this function. You can also click on utilization or displacement. So here, by clicking on the displacement, you can see where you can get the maximum displacement. The more purple, the more displacement. One good way to actually numerically understand these colors is to just double click on the grasshopper window and key in legend. Okay. Now you can connect the upper and the bottom extreme of that spectrum. So for the displacement, white represents zero displacement, and the very sharp purple represent this much of stress. Even for axial stress, if you click on axial stress, you can get the legend for compression to tension here. So that's also a good way of representing your analysis. For the beam view, you have two options to connect this analyzed model to the beam view and just like see all the axial stresses, or you can connect the beam view to the model that you already viewed through your model. The pros of connecting this model to the beam view is that here you already set the scale of the display of deformation. So then here you see, like in this case, the deformation and displacement of the beam is not that much visible, but here through this model view, you can see it better. One other thing that you can study is that when you, here under beam view, when you open up this section forces, you can click what you really want to read in the provided diagram. So I would say I want to read field, I want to see numbers, and I want to see also the moment diagram. Okay, we all did a lot of analysis to find the moments. So by clicking on MY, you're actually studying the moment about the y-axis. Okay, the rotation about the y-axis. So by clicking on that, you get such a kind of diagram like that, which is very big. So you can just reduce the scale of your diagram. Scale of the display of that diagram. It doesn't really interfere in the values. But yeah, I think 0.1 is something fine. Okay. Now here you can also read the maximum bending moment in your beam, which is minus 15.29. That's nice. And here you're also going to have some maximum moment at your column, which is here, 12.71. And you have a positive moment here, 12.71 there as well. If you play around with the joints and change their restriction, restraining modes along, like for example, x-axis for translation, or like y or z, well, that will be really crazy. Or if you restrain it along rotation, then you see, if you restrain all the rotations, which means that you're like making those connections very fixed, then the story will be different. You see, here you're not going to have any moment at the column, and all the moments will be carried out by the beam, and that is minus 28, which is almost what you manually calculated in a class. In a class, we imagine that everything will be handled by the beam, but not by the column. Here you can play around with different restraining mode of the connection of the beam to the columns and see what is the maximum bending moment in your beam and columns. Okay, you can also study shear. If you click on VZ, it gives you a diagram. So let me just turn off the moment and just study here is for um, the scale of the shear. So VZ represents the shear value all along your frame for your beam and the columns along the Z-axis. So here you can see that the maximum shear value that your beam will tolerate is at the connection to the column, and that is a maximum of 20 kilonewtons. Okay, so this first line scale is for the shear, whatever is represented in kilonewtons, which is the unit of the force, and kilonewton meter, which is like foot kips, like the scale of the moment. So you can turn on and off your shear and moment diagram and study that. So that's all about your model view and analyzing a very simple frame.